Super. All right, so welcome everybody. So today we're going to be going through the third lecture of our probability section. There's going to be one more after this, and this lecture is going to be overwhelmingly about probabilistic distributions, and we're going to be talking about different distributions, what they are, what's interesting about them, where they come from, and why they're worth knowing, essentially. There's a lot of them. So I've selected sort of what I think are some of the most important ones for us, and I've given you sort of a shopping list of them here. And so what we're going to be doing is essentially going through and looking at how you define each of these distributions, what's interesting or why these distributions are particularly useful. And that's essentially it for this lecture. It's going to be quite heavy on sort of practical looking at the forms that different distributions take and sort of their properties and why those are interesting or useful for us in physics and astronomy. So we're going to start off by talking about discrete distributions. We're going to go through a bunch of things like what is a random variable or a Bernoulli random variable. And then we're going to, after we've gone through a bunch of discrete distributions, we're going to sort of generalize a bit further to more continuous distributions, including, some things that you'll all be very, very familiar with and some things that you probably aren't so familiar with. So we'll go through them in quite a bit of detail. We're going to end this lecture after we've gone through these distributions, and then the last lecture on probability, which we're going to be doing not next week, obviously, because next week is a study break, but the week after, we'll be going through the sort of ways in which we utilize these distributions for modeling of systems of statistical systems and things like that. So talking about generating distributions of data from these particular distributions and things like that. There'll be a little bit of overlap conceptually, but mostly we're going to be focusing just on the actual analytic distributions today. Cool, so let's get started. Before we get into a discussion about probability distributions and all the different sorts of distributions that we have and where they come from, we need to talk first about a couple of definitional things that are pretty important. So the first of which is what's called the probability mass and probability density functions, PMF and PDF. And we've actually gone through PDFs and PMFs a little bit already without us actually naming them as such. So these are going to be things that I think you won't be super surprised to hear about or that you understand sort of innately. So when we were talking about probabilities, we've always been talking about, or we formulated our definition of probability as being the relative frequency of observations given a very large number of observations of a particular value, especially in the discrete sense. When we spoke about probabilities, we spoke about how many occurrences of a particular outcome do I have in the long run. And that was essentially how we created probability in our brains to begin with. What the probability mass function is essentially the formalization of that concept. It's the distribution of all possible outcomes and the probability associated to all of those various outcomes. So we can go back to the very, very first thing that we ever spoke about when we started looking at probability, and we started talking about the tossing of a coin. It was very, very simple. We started with just tossing a simple fair coin. And what we looked at, or what we saw was that if you have a simple fair coin, when you toss the fair coin, you have basically the outcome of it landing on tail, which I've assigned to the value 0 here, or the outcome of it landing on head with it landing, and I've assigned that to the value 1 here. And in the limit of very large n, the average of those things for a fair coin is equal. And so the probability mass function, rather, of this particular distribution is just a bimodal distribution at 0 and 1, which have equal probability. Okay. So this is the probability mass function. The probability mass function is defined explicitly for discrete variables where you have, discrete outcomes and you then assign a specific probability to each of those outcomes. For non-discrete distributions, the probability of any one outcome is always 0. Why is that? So if you have a continuous variable, the probability of getting a particular variable value is infinitely small, right? Because in a fixed interval of a number line, there's an infinite number of possible values that you can take. And therefore, the likelihood or the probability of taking any one of those values is infinitely small. So the probability mass function doesn't make a lot of sense for a continuous function because it's defined as being a probability of finding a particular value. Okay. And so instead, for continuous distributions, we talk about what's called the probability density function, PDF. And the PDF is defined as being the probability of finding a particular outcome within some finite range of values. Now, the way in which we formulate this in practice is by actually, taking it to the limit of an infinitely small interval and, using that to define the PDF. But the formal definition is that the PDF is the probability of finding a variable X between some limits of two variables A and B. And so you can think of that as just being the integral of the overall probability distribution between two limits. Right, so if the PDF is non-negative, we know that the probability distribution, so the actual value of probabilities has to be non-negative, right? Because you can't have a negative fractional occurrence of something, and that's how we formulated probability at the beginning. Because of that, because this value has to be non-negative, the probability density function also has to be non-negative. Okay, so because this thing here can't have negative values, the integral of that thing between any two arbitrary limits can't be negative, and therefore this can't be negative. Additionally, we know that because the probability is, again, this fractional representation thing, it has to integrate to 1. And therefore, if I was to take the limits here, A and B, to be -infinity and +infinity, then by definition, the integration of this thing over -infinity to +infinity has to be 1. And therefore, the PDF must also integrate to 1. Okay, so another simple sort of common sense conclusion that we can make about the PDF. All right, and so what we can do is we can construct a fictitious PDF. So we're going to do that to start off with, to get an idea or to get familiar with what the PDF is. So what I've done is I've created a fictitious probability density function of train delays from a completely fictitious railway company that's totally fabricated and doesn't exist. And that totally fictitious railway company is called Bochum. And what I've done is I've created the distribution of delays at Bochum. And what you can see is that my probability distribution here has a peak at around 5 minutes and a very, very long tail out to 2 hours. And there's a couple of important things about Bochum, one of which is that you'll notice that there is 0 probability of having no delay, which is, I think, a fair reflection of this particular railway, which doesn't exist. And there is some probability of seeing a delay within some particular interval. Okay, so we can integrate this distribution and calculate the probability of seeing a delay that is less than some value. Okay, and for that purpose, we can construct what's called the cumulative distribution function, something that we're familiar with, that we've learned about already. And if I take the cumulative distribution function of this probability density function, then what we find is that I can use the CDF here and calculate the cumulative probability of seeing a delay that is less than some value. So let's say I want to know what is the probability that I'm going to be able to board my train with a delay of less than 20 minutes. And so I can look at the CDF and I can just read off, okay, so the probability, the amount of probability mass that is less than a delay of 20 minutes is a little bit over 50%, call it 55%. And so therefore, the probability that our train is going to arrive with less than a 20-minute delay is a little bit over 50%. Or conversely, there's a 45% chance that you're going to be waiting longer than 20 minutes. So this is how you can utilize the probability density function and the cumulative density distribution function in order to estimate probabilities around particular values of a variable. Okay, it's something that we're going to be looking at quite a lot today. And the last thing that we need to remind ourselves of is the quantile function. So you'll recall the quantile function was, again, something we've looked at somewhat at length. And what it tells us is, given some question of probability, what is the value of my, my PDF at that integrated probability? So it's basically the inverse of this function, or in this case, it is the inverse of this function, because this is an analytic cumulative distribution function, not an empirical one. So it is invertible. And what we can do is we can do exactly the same process. I can say, what is the delay at the median of my probability distribution function, for example, and I have a probability of around 20, just under 20 minutes. So at the median wait time in my probability distribution function is of order 20 minutes. Can you spin the CD? I'm not sure I understand that question, but I think that's kind of where we went with the CD, with the quantile function. But feel free to ask again if that's not clear. Cool. Right. So those are sort of the important things that we've largely already looked at. Okay, we're already familiar with some of these concepts. We're not really surprised by any of the things we've seen so far. Now we're going to talk about something that we haven't seen yet, and it's going to be quite important for the remainder of this lecture. And this is the concept of the expectation. So in the first section of this course, when we got very started into section 1, we started looking at the mean and the standard deviation and the variance. Okay, and we were quantifying those things in terms of the sample of observations that we had. So we took a sample of observations and we said, what is the mean? What is the standard deviation? What is the variance of these particular observations? In that sense, what we were looking at there were descriptive statistics. They were statistics designed to describe the data set. What we're going to formulate now is how we can use the same statistics, but instead of describing the distribution of actual observations that we have, but describing instead the distribution of the probabilities that those variables have been drawn from. Okay, and in that sense, what we're doing now is we're going to be describing the probability distribution itself from which we draw the random variables, and these are called the expectations. The expectation is given this symbol, the funny capital E, and we can define the expectation value of a discrete variable. So this is discrete finite values within some sample space omega, and coming from a probability distribution P. So this is coming from a PMF, which is we've assigned P, as being the expectation of X is equal to the sum of X times the probability at X. Okay. For continuous data, you have basically the same thing, except instead of being a discrete summation, it becomes an integral. And that integral, again, is just the integral over the entire sample space omega for X times the now probability distribution P, little p. So it's an important sort of thing that you might get confused about. So let's clarify it quickly. Generally speaking, when we talk about discrete probability values in statistics, we use the capital P. And when we talk about probability distributions, we use the lowercase p. Okay, hopefully that's clear. So let's actually do this in practice. Let's take a fair dice roll. Let's compute the expectation value of a fair dice roll and see what we get. So I've assumed a fair six-sided die. So that is to say that the probabilities, so we're up here, we're looking at the individual probabilities of our PMF is 1/6 for I is in 1 to 6 because it's a six-sided die and every side is just as likely to come up. And so we can calculate the expectation value. Now, I know that these formulae can look a bit daunting at times, but they're really quite simple. The expectation value of this six-sided die is just the summation of the value times the probability of seeing that value. So it's 1 times a sixth plus 2 times a sixth plus 3 times a sixth all the way to plus 6 times a sixth. It's really quite simple. We can then pull out the sixths and we can see that we have 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. But that's the same as 1/n times the summation of xi from I equals 1 to n. And that you should all recognize as being the arithmetic mean. So the expectation of an arbitrary value of variables, the expectation of a probability distribution given a sample of random variables is the arithmetic mean. Okay, that might sound convoluted, that we've just basically come up with a completely new way of saying, I know what the mean is. It's going to become quite useful as we go through today's lecture. So the expectation value is the arithmetic mean of the probability distribution. Okay. We can then also calculate the variance. The variance is going to be something that is always very important in statistics, but is particularly going to be important when we start looking at some different distributions. And the variance we define as being the expectation of the squared deviations from the expectation. So this is the same formalism that we came up with for the variance in section 1, except now instead of showing the mean of the value minus the mean all squared, I'm showing it in expectations. Okay, so we have the expectation of x minus the expectation of x all squared. You can then take this and just do some simple math and reformulate it into the variation, the variance of x is equal to the expectation of x squared minus the square of the expectation of x. And this is quite easy to calculate, this thing here. So it's quite useful frequently knowing this particular formulation of the variance. So for example, we can take, well, I haven't done it here. I'll leave it as an exercise. We can take the same example that we've got here with the dice roll. We can calculate the expected variance of the dice roll. And, you know, I'll leave that for you guys to do. I'll fill it in the lecture notes, but for now, I'll leave it for you guys to do. The last thing that we can calculate is the covariance. And the covariance is, again, something that we've already seen. But last time, we said that the covariance, we're just going to define it like this. We didn't really explain why. And the reason that we're defining the covariance the way that we did is because of these expectations. So what we're going to do is we're going to define the covariance as being the expectation of, as being the expectation of the variation with respect to the expectation in the x dimension times the variation with respect to the expectation in the y direction. Okay. And then again, we can reformulate this, and we end up with the covariance of x and y is equal to the expectation of x times y minus the expectation of x times the expectation of y. And so this is the formula for the covariance, the definition of the covariance. And we'll remember from the beginning of section 1 that if you have two independent variables, the expectation of, the arithmetic mean of the two variables multiplied together is the multiplication of the two arithmetic means, which means that the expectation of xy is just equal to the expectation of x times the expectation of y. If we sub that back into here, obviously we get this, this term is minus itself, and we end up with the covariance of x and y is equal to 0, as you expect for independent observations. Okay. All right. So that's the expectation. That's how we can calculate the expectation of a probability distribution and the variance of a probability distribution given these two formulae. Something that we're going to do quite a few times today. All right, great. So the first thing that we're going to discuss in terms of our probability distributions is the concept of what's called the Bernoulli random variable. Again, this is something that we've come across a lot already, but that we haven't put a name to yet. And so a Bernoulli random variable is any variable that has two possible outcomes. Yes, no, success, failure, 1, 0, whatever you want to call it. If you have a variable which has two possible outcomes and they have those, and they fall into those outcomes with probabilities p and 1 minus p, then you're talking about a Bernoulli random variable. Okay, and so therefore x takes the form of, you'll remember the little squiggle from our notation at the very beginning of the course. So the little squiggle means takes the form of, or is a random variable drawn from the distribution of, for example. So x takes the form of Bernoulli random variable, which is determined by the probability p. Then it has the probability density, or the probability mass function rather, of x is equal to x is 1 minus p if x is equal to 0, or is p if x is equal to 1. So that is to say, if I have a Bernoulli random trial and it's a fair coin, for example, and I'm tossing a fair coin, the probability p is 0.5 because it's fair. It's equally likely that I'm going to find 1 or a 0, head or a tail, success or failure. Therefore, the probability distribution for the probability mass function is just 0.5 if it's 0 and 0.5 if it's 1. If I have a biased coin, then the probability will not be equal to 0.5. It'll be equal to, say, 0.8 if it's more likely to find a head than a tail, in which case the probability of finding the tail is 0.2, the probability of finding the head is 0.8. Okay, so that's a Bernoulli random variable. The cumulative distribution function of this is then, trivial because it's two discrete objects. It's just 0 if your variable is less than x, if your variable x is less than 0, because obviously this is only defined at 2 points, x equals 0 and x equals 1. If you're between those two variables, those two values rather, then you have the cumulative value 1 minus p. And if you're greater than unity, then you have the cumulative value 1. Okay, pretty simple. We can then calculate the expectation of a Bernoulli random variable. Okay, and we can do that in exactly the sort of way that we've been doing on the last slide. So we take our expectation formula and we say the expectation of x is the sum over all possible outcomes, x times the probability of x. In this case, there's only two possible outcomes. Either x is 0 here and has a probability 1 minus p, or it is 1 and has a probability p. Obviously, multiplied by 0 cancels, and you end up with the expectation of x is just p. Okay, so the expectation of a Bernoulli random variable is just p, the probability. The variance we can calculate in the same way. So we can take our formulae again. We have the variance of e to the x squared minus the expectation of x all squared. And if we just plug these in, then what we find is that the expectation of x squared is equal to x squared times the probability of x at x squared minus the probability of the expectation all squared. Now we know this is already P. We just calculated it here. This thing is, we can just plug in the formula again. So we end up with 0 squared times 1 minus P plus 1 squared times P. And you end up with P minus P squared, or P times 1 minus P. So the variance of a Bernoulli random variable is P 1 minus P times 1 minus P. And that's a, you know, an important thing for you to know, for you to remember. One last observation is that if P is equal to 0 or equal to 1, then the expectation is just P, as it always has been, but the variance becomes 0, right? Because either you get 0 times 1 or 1 times 0, and you end up with 0. And in that circumstance, the Bernoulli random variable follows what's called the degenerate distribution. The degenerate distribution is that which has only one possible outcome. There is no randomness involved. So you can think of tossing a coin that has heads on both sides, right? There is one outcome. You are guaranteed to get it. And therefore, you follow the degenerate distribution. The degenerate distribution has expectation P, which is either 0 or 1, and has 0 variance, because by definition, there cannot be any variance because the outcome is guaranteed. Okay, hopefully that's all fairly clear. Cool. The Bernoulli random variable is useful because it informs us about things which happen over, you know, a discrete 1-0 success failure thing, and there's lots of those. Right? We can come up with, you know, any number of possible experiments where we're only interested in whether or not there is a success or a failure. Think whether or not you make a detection in a cloud chamber, whether or not, you know, your muon detector detects a signal from a cosmic ray cloud. Word has left my brain. Cosmic ray scattering event through the atmosphere. Shower was the word I was looking for. What we can then do is we can ask the question, if we have a series of Bernoulli random variables, or rather a series of trials, all which follow the Bernoulli random variable, how many throws or how many trials do we need to do before we see a success? Okay. And so if we have a Bernoulli random variable and we ask the question, how many throws do we need to do until we observe the first success? That probability distribution is what's called the geometric distribution. So let's take a coin. We have a biased coin. We don't know what the probability of the biasing is. We just know that it's something between 0 and 1. It's either never going to throw a head or it's always going to throw a head, and it's somewhere in between. And we're going to flip this coin until the first head appears. Okay. The number of flips that we have to make is one of these Bernoulli, is a discrete random variable. Each flip is a Bernoulli random variable, and it has some value greater than or equal to 1. Okay, because when you flip your coin, you either see a head in the first flip and then you stop, so it is equal to 1, or you don't, and you throw tail, tail, head, then it's 3, etc., etc. So this is a uniform, this is a discrete random variable that is a positive integer. And each toss of the coin has a probability of being a head P. And so naturally a probability of 1 minus P of being tail. In order for us to observe n tosses, in order for us to observe n trials, we must have observed n minus 1 failures, because otherwise we would have stopped already, right? And therefore, the probability of observing n throws prior to hitting a head, prior to hitting a success, is just 1 minus P to the power of n minus 1 times P. Okay. Now we can think about this in terms of a few limiting scenarios. Let's imagine a coin that has obviously well, let's think of the two most obvious limiting cases. We pick up a coin on the ground. We don't know what its probability of heads and tails is, but it turns out this coin has no head, right? And we just flip and we flip and we flip and we flip and we keep going until we see a head. What's the probability of observing n is some integer that is less than infinity, right? Because there's no head, the probability of observing a success is 0, and therefore the probability of observing any n as being the success is 0. Okay, makes sense. The opposite is also true. If you have a coin that just has heads on it, the first time you throw the coin, you end up getting a success. And so the probability of seeing n equals 1 is 1. But the probability of seeing anything larger is 0 because you never continue the trials beyond a success, right? So it's not defined after n equals 1, basically. So this is the probability mass function of the geometric distribution. As I said, it's defined for positive integers, and obviously because it's a probabilistic distribution, p has to be less than or equal to 1, or between 0 and 1. We can then go through the exact same process that we've done here. I haven't done this for every single distribution that we're going to look at because we'd be here for a Hubble time. And instead, what I've done is I've just shown that the expectation of the geometric distribution is p, and the variance of the geometric distribution is p times 1 minus p. If you're interested, please feel free to go and check and verify these things yourself. They aren't super complicated to calculate, especially for these discrete distributions, and it might be just a good exercise to convince yourself that you understand what's happening, the expectation. The next distribution that's relevant is a slightly different take on a series of trials of a Bernoulli random variable. So instead of asking how many throws do I have to do before I see a success, we can ask a different question, which is how many times do I see a success in n throws? Okay, and that distribution is what's called the binomial distribution. Okay, so it's the number k of successes that you see in n trials, and the probability of seeing k successes in n trials. Okay, now obviously the probability of seeing k successes is p to the power of k, right? Because, you know, we have a probability of seeing success, which is p, and I throw my coin n times, and so the probability of seeing k successes is p to the power of k. The probability of seeing n minus k failures is the probability of 1 minus p to the power of n minus k. Okay, again, because we've thrown n minus k failures, and therefore the probability of doing that is 1 minus p to the power of n minus k. However, crucially, there are n times n minus 1 times n minus 2 times n minus k plus 1 ways of constructing k successes from n trials, right? This, however, is something that we've already seen. You might remember. This is the formulae for constructing k successes when order of appearance doesn't matter. So I don't care whether or not the first toss that I throw is a success. All I care is that in my n throws, I saw k successes, right? And so this is what we defined previously as this n choose k thing. We'll get to that in a sec. So the probability of observing k successes from n trials is this thing here. Is you can reformulate this coefficient here as n factorial over k factorial n minus k factorial, this thing here, which, spoiler, is called the binomial coefficient, right? So this is where this n choose k comes from. It's the binomial coefficient. And so the probability of observing k successes given n trials and a probability of success of p is equal to the binomial coefficient n choose k times the probability of success to the power of k times the probability of failure to the power of n minus k. So this is the binomial probability density function, or PMF rather, because it's a discrete thing, so the probability mass function. And again, this thing out the front we call the binomial coefficient, n choose k. We can look at we can take the binomial function, and again, we can calculate the expectation, and we find that the expectation of the binomial function is just n times p. Calculating this is pretty easy. Yeah, you'll see when you do it that, you know, a bunch of things fall out and you end up just with a multiplication or a summation over p, which gives you this np. Well, I mean, we could do it by hand if we wanted to. Essentially, the way to think about this is that the number of each trial is a Bernoulli random trial which has expectation p, right? Therefore, if I throw n trials, the expectation should scale and you end up with np. But you can do it yourself. It's quite simple. And the variance of the binomial function is n times the variance of the Bernoulli random trial again. All right. We can take the binomial function, which we just defined as being for only two outcomes, right? A Bernoulli random trial. And we can extend it to allow for multiple different outcomes. Okay, so instead of having a single possible outcome, we can have n possible outcomes, all which have their own probability assigned. So the obvious, sort of the simplest thing that we can imagine like this is the rolling of a dice. Okay, so we don't now have a coin where we have two possible outcomes. Instead, we have a die which has 6 possible outcomes, and we have each ith outcome has some distinct probability. Now, on a fair die, they're all the same, and we basically want to ask the question of you know, what is the probability density function of observing outcome 1 n times, 2 n times, outcome 2 n 2 times. Ooh. And basically, this distribution follows what's called the multinomial distribution. Okay, and so we have, for example, n occurrences of the first outcome, n2 occurrences of the second outcome, nk occurrences of the kth outcome. And those things happen with probability p1, p2, all the way through to pk. And there are capital N total trials. So the sum of n1, n2, n3, all the way through to nk is equal to n. Okay, that's what's shown here. The probability mass function of the multinomial distribution, this thing here, is this coefficient, which is now called the multinomial coefficient, right, as opposed to the binomial coefficient, which we had before, multiplied by the probabilities of each possible outcome to the power of the number of observations of that outcome. Okay, so this is called the multinomial distribution, and we can do this to basically demonstrate something that we saw all the way at the beginning of this course, which was, as I said, the rolling of die. So let's say we roll 2 die, and we want to know what the sum of those 2 die are. Now, what we did previously was we brute forced this by hand. We actually pretended that we rolled a whole bunch of die and we looked at the distribution. But now we don't have to do that. We can do it analytically because we know that that distribution is the multinomial distribution. And so we can actually look at the probability mass function of the multinomial distribution, and we can see that indeed it follows this distribution that we saw when we did our random trials at the beginning of the lecture course. The multinomial distribution has a couple of has a different expectation and a different variance for each of the possible outcomes. The expectations, however, of each of the outcomes are just the expectation of the binomial chance of that particular outcome. So the expectation of xi is equal to n times the probability of the ith outcome. Okay, going back to these probabilities here. All right, so that's the multinomial distribution. Making good headway, making good progress. The next discrete distribution that we're going to talk about is a really important one. It's called the Poisson distribution. So let's consider an experiment where we know that the number of occurrences of an event happens, where we want to know the number of occurrences of an event that happens within some fixed window of time. Okay, so we can imagine that this is, for example, like a decay process where we want to know the number of decays that we expect to witness from a given atom in an hour, for example. Okay, we're interested in counts per hour. Okay, so because it's a count, this has to be a discrete variable because you can't have non-integer counts. And so it's going to be, positive integers. We can make two additional limiting constraints on our experiment, and that is to say that the decay process happens with some fixed rate. Okay, so it doesn't change over time. The probability of seeing some emission is fixed. And that the time between the events, the time between the decays is independent of the interval from the last decay. Okay, so this isn't like our geyser that we discussed in previous things, where there's a correlation between the time between the last event and the next event. Okay, this is now completely independent. So there's no correlation between the time of the emission and the time of the previous emission. Given these constraints, the number of observations that we expect to see per interval of time follows what's called the Poisson distribution. Okay, and the Poisson distribution is we expect to see k observations, or rather k is drawn from the Poisson distribution, which is determined or governed by a parameter which is called lambda, which we call the intensity parameter. And the probability mass function of the Poisson distribution is e to the power of minus lambda times lambda to the power of k divided by k factorial. So this thing here is the probability of seeing k observations in our time window given an emission rate, or rather an intensity lambda. Okay. This lambda, therefore, is pretty important. So what is it? Well, we can actually calculate the expectation value of our Poisson distribution. So we're going to go back and actually do this one. We're going to calculate the expectation of the Poisson distribution. So we have our expectation formula. Again, it's discrete. So this is just a summation. And we can see that the summation over, it goes from x equals 0 to x equal infinity. But at x equals 0, you have a 0 here and the value turns to 0. So I've just dropped that particular occurrence and said, let's start summing at x equals 1. And we sum from x equals 1 to infinity. Now, we can divide top and bottom by x in order to get, we have this, this modification to the probability here, so to the expectation. We can then pull out all the things that aren't dependent on x. Right, so we can pull out the e to the power of minus lambda and one of the lambdas to give us a lambda here, x minus 1. We can then actually produce this summation, right? So we can calculate this, expand this out, and we end up with lambda to the power of 0 divided by 0 factorial plus lambda to the power of 1 plus 1 factorial, et cetera, et cetera. But this thing here is, 1, so drops out. And we end up with the summation of x equals 0. Actually, we can change this. So we just end up with the summation from x equals 0 to infinity of lambda to the power of x divided by x factorial. Now that probably looks familiar to some of you, because that is the expansion of the exponential distribution. Okay, so this thing here is just equal to e to the power of lambda. So we can put that back in here. And all of a sudden, we end up with lambda, e to the power of minus lambda, e to the power of lambda. These things cancel, and you just end up with the expectation of the Poisson distribution is equal to lambda. So the expectation of the Poisson distribution is equal to the intensity parameter, the thing that determines the shape of the Poisson distribution. It's fundamental, very, very important point, property of the Poisson distribution. You can also do the exact same process with the variance, which I'm not going to do here. Leave it to you to do in your own time. But what you find when you do that is that the variance of the Poisson distribution is also lambda, which is surprising. And so the Poisson distribution has the very, very unique property of having an expectation and a variance that are both equal to lambda. Okay, it's a fundamental property of the Poisson distribution. All right, so we can calculate the Poisson distribution for a range of different lambdas, so you can actually see what it looks like. And again, it's a discrete random variable, so I've shown it here as spikes, the probability mass function. And you can see that, for example, with a lambda of 1, the expectation we know is going to be equal to 1, and the variance is going to be equal to 1. Now, we know the expectation is the arithmetic mean, so we can basically just do averaging by I here. And sure enough, the average is about 1, looks to be about 1. The amount of mass on the left of 1 and the right of 1 looks about the same. Similarly, if we look at the Poisson distribution with intensity 5, it peaks at around 5, same sort of story, and 10 peaks around 10. So again, this is sort of demonstrating that what we've just formed by math is actually true. And so we learned something about the Poisson distribution. Now, I said at the beginning that the Poisson distribution is really important. And the reason why it's really important is that because frequently what we're actually measuring isn't some truth value, like we're not, biologists measuring a particular sample of something and doing thousands of iterations. What we're doing is we're taking an observation of a physical process and using the number of observations of that physical process in a specific time window to inform us of the probability distribution of that thing that we're interested in. A really simple example of this is the observation of fluxes, right? So if you're an astronomer and you're observing the light coming from a galaxy or from a star or from whatever, from a light bulb, the flux that you measure is the integration of the number of photons that arrive at your detector in the time interval that you observe for, right? And that the uncertainty or the noise on that parameter is determined by the Poisson distribution. Okay, so for example, if I take a very, very short observation, then the expected number of photons that are going to hit my detector is going to be small. So the expectation is going to be low. The expected number of photons hitting the detector will be low. The variance is going to be equal to the expectation, right? And so the variance is also small, or let's say it's 1. Let's say the expectation is 1, the variance is also 1, right? If, however, I keep the shutter open for a very, very long time, and I just let photons continually fall into the bucket and hit my detector, then what I find is that I'm going to have some peak, which is going to have an expectation of however many photons I expect to see hit the detector in that time interval, because the time interval has changed. The rate hasn't, but the time interval has changed, and that's changed my Poisson distribution. And therefore, I get a different statistical distribution of photons. because I've changed the time interval of my observation. And that changes the uncertainty on each observation, of each pixel, of each detector element. The place that this is particularly relevant is in the high energy regime. People who study gamma rays in an astrophysical context have detectors that essentially catch one photon at a time, because gamma ray photons are relatively rare in an astrophysical context. And therefore, when you point a telescope at a gamma ray source, you expect to see few actual photons arriving at your detector and being able to be detected. And so those observations are very, very often heavily Poisson noise limited. They are determined that the noise and the uncertainty on seeing an observation is determined almost exclusively by the Poisson distribution. Okay, but it's not just true for like I said, for wavelengths. It's true for photons. It's true for any observation that you have when you're looking at the number of incidences of an occurrence in a particular window. Crucially, that window doesn't have to be time, right? I can equally construct a Poissonian distribution using spatial intervals, not temporal ones, right? And so let's sort of flesh this out a bit. The number of expected occurrences of a Poisson variable in some period is t. Okay. With in some period t is lambda, is the expectation of that thing. If we expand the interval to be twice the size, we naturally intuitively expect that the number of observations, the expectation of the number of observations also increases by 2, right? So we end up with a distribution that has a double the number of occurrences because we've doubled the interval. But like I said, this doesn't need to be restricted to temporal events. So if I take a Poisson variable that is defined in space, so let's say I take the number of insects that I find per square meter in my backyard. Okay, let's say that the insects are distributed randomly, so they don't group together for some reason. The number that I find in 1 unit area is lambda from my Poisson distribution. The number that I find in 2 times the area is 2 times lambda, because they're randomly distributed. And so the Poisson distribution has a fundamental link to randomly distributed objects. Because if I have some domain, some area, call it my backyard, call it time, call it whatever you want, and observations in that domain are totally random, right? Then the probability distribution of observing a subset, a particular subset of that domain, is the Poisson distribution. That's what we just figured out from our little insect example, right? And from our time of observations things. And so many models that we have in physics and astronomy use the Poisson distribution because it allows us to assume that the observations that we're seeing are a subset of a truly, totally random distribution that we don't know. The domain is, all galaxies in the universe, and the probability of seeing a set of uniformly, randomly distributed objects in a particular volume of the universe, if there's no clustering or anything like that, is the Poisson distribution, right? The probability of finding particles that are uniformly distributed in a container in a subset of that container is governed by the probability, by the Poisson distribution. Can we use Poisson statistics also for counting sources in a given area and flux range? Yeah, so exactly. So the Poisson distribution tells you the probability of finding K objects in some unit volume area, whatever, of your domain, right? Given some rate, given some intensity lambda. So that's exactly what it's for. So that's a good question. Yeah. All right. Hopefully that's somewhat clear. If not, obviously feel free to ask questions. We're now going to sort of change gears a little bit. We're going to move away from discrete variables, and we're going to look at some continuous variables. Now, there's lots of these that are really important. So we're going to buzz through a few of them. The first, or the simplest, continuous distribution that you can possibly come up with is the uniform distribution. The uniform distribution is given the symbol U between some limits A and B. And as the name suggests, it takes the value, it takes equal probability at all values between A and B. Yeah. So the probability of observing a value X is if the probability X is less than A, then obviously it's 0 because you don't have any probability outside the limits of the uniform distribution. If it's greater than B, also 0. And if it's in between, the probability is 1 over B minus A. Now, why is it 1 over B minus A? It's because the probability distribution has to integrate to 1. Yeah. So if A minus B is 0 and 1, if A and B are 0 and 1, which is shown by my red curve here, then the probability of all values between A and B is 1, because the integral of this red curve has to be 1. The same goes for a different uniform distribution that goes from -2 to 1.5. Okay, it's still 0 outside those limits, but it has the amplitude within those limits of 1 over B minus A. And again, the same goes for an even broader distribution. So this is the uniform distribution. The uniform distribution has expectation A plus B over 2, which probably makes sense. It's the middle of the uniform interval, right? Not terribly surprising. One thing that might surprise you or will surprise you is the variance of the uniform distribution is B minus A squared divided by 12. Where that number comes from, I'll let you figure out yourselves when you do the variance calculation. But what that means is that the standard deviation of a uniform distribution is the width of the distribution divided by the square root of 12. Okay? That turns out to be important sometimes, especially when you're using, for example, kernel density estimates, where we specify, for example, that we want a rectangular kernel and you want to know how wide that kernel should be. But the way in which you specify the width of the kernel is by giving the bandwidth or the standard deviation to the function. Okay, and this is quite common because if you have an arbitrary kernel, you don't want to be specifying it differently for the uniform distribution as for the Gaussian distribution. You just want to say, I have a kernel, the variance of that kernel is this value, please give me the kernel density estimate. Okay, and so when you use a uniform kernel, you always have to divide by this square root 12 or 12, depending on whether you're providing the standard deviation or the variance. Silly thing, will confuse you if you don't know it in advance. All right, so we can calculate some stuff using the uniform distribution. So let's say that we have a scenario where the tram to the RUB arrives at the Bochum Hauptbahnhof every 5 minutes during peak travel. Okay, so that's our setup. The tram arrives at the station every 5 minutes to take you to the university, which, you know, obviously not right now. If people arrive at the station randomly, So people don't look at the schedule. They're very busy people. And instead, they just arrive randomly at the station. The waiting time that they have to wait on the station is therefore a uniform random variable. It's a uniform distribution drawn from the uniform distribution of 0 to 5, because if they arrive just as the last train left, they will wait 5 minutes. If they arrive a second before the train arrives, they will only wait a second. Okay. So the probability of waiting is just 1/5 for all values between 0 and 5, and it's 0 otherwise, because you can't wait negative times, and you can't wait more than 5 minutes. What's the expectation of my wait time? If the tram arrives every 5 minutes, the expectation is going to be 5 divided by 2, which means that the expectation is 2.5 minutes. Yeah. We can also use the cumulative distribution function, which we spoke about earlier, to calculate the probability of waiting less than 2 minutes, for example. That's a good question. The question is, does it not need to be less than 5? The uniform distribution is defined as being up to and including the limits. And so the maximum possible wait time is defined as being, you arrive, for example, just as the doors shut, right? That's your lower bound. And that gives you a full 5 minutes until the next doors open. So it's inclusive of the limits. The uniform distribution is inclusive of the two limits. Yeah, good question. So we can use the cumulative distribution function to calculate the probability of a value less than some x, which is really useful for calculating how long, or what's the probability that I have to wait less than some period. Now, because the uniform distribution is a really simple distribution, there's actually an analytic formula for the cumulative distribution function of the uniform distribution, and that's x minus a over b minus a for all values a is less than x is less than b, and is equal to 1 for all values greater than b, again, because it's a cumulative distribution function. And so the wait time for our train is just equal to x over 5, which means that there's a 20% chance of waiting less than 1 minute. Okay, given that a train arrives every 5 minutes. And you can do this again for whatever sort of setups you want. Cool. The next distribution we're going to look at is one that we've seen before, but that I don't expect that you're familiar with. And in fact, many of you ask, what is that function when we first saw it? So here's learning about it. So the second function is called the beta distribution. The beta distribution is not something that you will come across in, much in nature necessarily. It's an extremely flexible function though. And because of its flexibility and because of something else, which is not going to make any sense to anyone now, but will become very important in the next section of our course, the beta function is very, very useful as a statistical distribution. Okay, the beta function is defined using two shape parameters called A and B, or alpha and beta, depending on where you look, and is defined as the gamma function of alpha, or A, times the gamma function of B divided by the gamma distribution of A and B. Now, what is this? Well, the gamma function is for integer values is just n minus 1 factorial is the formula for the gamma distribution for integers. Sorry, the gamma function for integers. For non-integer values, and actually for any value that is complex and has some positive real component, the gamma function is defined using this integral here. And again, as I said, is valid for any positive real component. This thing here on the bottom, we're actually going to see next, is called the gamma distribution. But the thing that's really interesting or really, really useful about the beta distribution is that its shape is very, very flexible. So the beta distribution is defined on a finite range. It's defined between 0 and 1, which you can then transform to any finite range you like, naturally. But the utility of the beta function is that it's the shape that it takes is very, very versatile. So if you have identical shape parameters, so 1, 1, 10, 10, 50, 50, then the beta distribution follows sort of Gaussian-like distributions or a uniform-like distribution for 1, 1. If you have different shape parameters, then it can take lots of different forms. It can take things that look sort of exponential, that look like they have some skewness to them. There are, very, very low skewness, but shifted in the mean to one side of the 0 to 1 region, et cetera, et cetera. So the beta distribution is really, really versatile. You can use it for a lot of stuff. It's got the expectation of A over A plus B, and variance of AB over A plus B squared, A plus B plus 1. So you can calculate those yourself if you're interested. Another similar function that's really useful is the gamma distribution. The gamma distribution being that thing that was just on the denominator of the beta function. And the gamma distribution, again, is useful for this thing we're going to talk about next section called conjugate analyses. And it's defined using, again, 2 parameters, but the 2 parameters here are the shape parameter, alpha A, and the scale parameter S. Now, the gamma distribution has the probability density function of this thing here. It looks very complicated, but like the beta distribution, it's really, really flexible. Unlike the beta distribution, it doesn't have a limit. It's not defined over a finite range. And that means that I can use a bunch of different values of the shape and scale parameter in order to construct the exponential distribution, for example, shown as the shape parameter is equal to 1. Or I can use it to form something that looks like a Gaussian or something which has more skewness and has a greater extent. So again, very, very versatile distribution. Not going to be super widely used until we get to the next section, but worth knowing about now. The next distribution we're going to look at is something that you guys have absolutely all seen, because we've already discussed it somewhat at length already in this course, but it is extremely important, and so is going to take up essentially the remainder of this course, this lecture. The Gaussian distribution, also known as the normal distribution, is, as I said, is basically one of the most important distributions in statistics. And what we're going to do over the course of the next 15 minutes, roughly, is figure out why it's the most important distribution in statistics. So a random variable which follows a Gaussian distribution with mean mu and variance sigma squared has the PDF. It's drawn from the normal distribution or Gaussian distribution of mu and sigma squared, and it has the probability density function 1 over the square root of 2 pi sigma squared times e to the power of minus x minus u squared 2 minus 2 sigma squared. So this is not something that will surprise you. It's something that you've all definitely seen before. The cumulative distribution function is defined as this. This is actually the formal definition of any cumulative distribution function, but we're framing it in terms of the Gaussian here. So the cumulative distribution function of the normal distribution of the Gaussian distribution is given the symbol capital phi, and the cumulative distribution function evaluated at some value x is the integral from minus infinity to x of this probability distribution function here. There's no analytic formula for that integral. Okay, so in practice, we do it by numerical methods or by computational methods. But it is really useful to know the cumulative distribution function and that you can evaluate it numerically, because it turns out that you can use the cumulative distribution function and a simplified version of the Gaussian distribution to do some really, really useful stuff. So the first thing we're going to do is we're going to define the standard normal distribution, the standard Gaussian distribution. And that's something, again, we've already seen. It's this Gaussian, which has mean of 0 and standard deviation of 1. You'll remember from when we talked about standardizing distributions in section 1, we talked about removing the mean and dividing out the standard deviation or the variance of the distribution. And that's what we're doing here. we have a special Gaussian that has a mean of 0 and a standard deviation of 1. That special Gaussian has a simplified probability distribution, probability density function, because obviously the mu's and the sigmas all drop out. And so we end up with this simplified function that we can also then calculate the cumulative distribution for. The thing that's really important is that it's possible to take any Gaussian distribution and convert it to the standard Gaussian distribution using what's called the Z transformation. The Z transformation is this thing here, and as it's exactly what we've already seen before. You can take a distribution of Gaussian observations, which have mu, mean mu, and variance sigma squared, and you can define a new variable called Z, which is the variable, the observation minus the mean divided by the standard deviation. And that new variable Z will follow the standard Gaussian distribution. Okay, so this is something, again, we've seen before. The reason this is super useful is because it allows us to come up with a particular property of the Gaussian distribution that is very, very important. The cumulative distribution function, or rather the probability of an observation being less than some value B, is the same in the normal distribution as we can do the Z transformation, and we end up with is X minus mu divided by sigma is less than or equal to B minus mu divided by sigma. This is obviously the Z score, right? We just did that same transformation, the Z transformation. And what this is then, this thing here is just the cumulative distribution function, this thing, where X is equal to B minus mu over sigma, right? So this thing here is defined as this cumulative distribution, this value of the cumulative distribution function of the standard Gaussian distribution. So the probability of a random Gaussian variable being less than some value is exactly the same as the probability of the standard Gaussian below the same Z score. Put another way, if B is chosen specifically to be 1 sigma, right? A 1 sigma positive deviation from the mean. The probability of this 1 sigma deviation of an arbitrary Gaussian with an arbitrary centroid and an arbitrary scatter is the amount of probability mass stored below the standard Gaussian distribution integrated from -infinity to 1. Okay, and so this gives us the ability to quantify the probability of any variable drawn from any Gaussian distribution in terms of the standard Gaussian. And that's extremely powerful because it means that we can interpret every single arbitrary mu sigma squared Gaussian in terms of probability, and the values drawn from them in terms of probability, in terms of where they sit, in terms of their Z-score, in terms of their number of standard deviations away from the mean. You can then also use symmetry constraints to basically show that these things are all true as well. I'm not going to go through them. Most of them are pretty standard and pretty obvious. Like, for example, given what we just showed here, the probability of it being greater than some value is just 1 minus the probability of it being less than that value. Makes sense, et cetera, et cetera. You can also extend the Gaussian distribution and all of these arguments that we just made to the multivariate scenario, where instead of having one variable, a univariate Gaussian distribution, we instead now have a multivariate Gaussian distribution, so Gaussian that varies in more than one dimension. The main thing that changes when we go from the univariate distribution to the multivariate distribution is that we lose the sigma squared that we had, and instead we now have this thing called capital sigma. Capital sigma being the covariance matrix. Now, you'll remember that we spoke about the covariance matrix before. The covariance matrix of n variables is the variance of each of the n variables on the diagonal and the covariance of those two variables on the off diagonals. And the covariance encodes this degree of mutual deviation that each variable has with each other. So if we have two independent Gaussian observations, totally independent, no covariance, right? Then we have a set of observations, X, drawn from a multivariate Gaussian with dimension 2 that has mean mu in each one of the dimensions and the covariance matrix sigma, capital sigma. Mu here, I'm going to assign to be -2 and 3. So the first dimension has a mean of -2 and the second dimension has a mean of 3. And the covariance matrix I said was independent. So there is only variance terms and no covariance terms. So all of the off diagonals are 0, and we end up with the covariance matrix just being a simple diagonal matrix. If I then plot the distribution of this covariate Gaussian in terms of x2 and x1, this is what I see. I see this covariate Gaussian that I expected. Everything looks good. Notice that because I gave a stronger variance to the first dimension, we have a flattening of the distribution, but these are still independent. There's no correlation. There's no twisting of the distribution so that information about x1 gives you information about x2. Zero covariance. We can make exactly the same distribution now for the covariate case. I've kept the same means, but now I've given some covariance to the two variables. And what you see now is that information about x gives me some information about x2, right? Because if I know I'm at negative values of x1, then I'm going to be probabilistically more likely to sit at smaller values of x2, right? There is some covariance between these two things. One of the things that you've all undoubtedly noticed in your courses and in your academic careers to date is that natural scientists use a lot of Gaussians. They are everywhere. Why? Why is it that the Gaussian seems to pop up all over the place? Is it basically because we decided at some point as scientists, we all got together and we said, you know what, we're all just going to use the Gaussian from now on. There's too many of these distributions. I'm sick of looking at them all. I just want to use the Gaussian, and that's all we're going to use. Everyone agree? Good, we're done. That's obviously not what happened, right? The reason why Gaussians are so common in the natural sciences has a physical reason. It has a mathematical, a statistical basis. And that basis is what's called the central limit theorem, CLT. This is the most important thing in this lecture. So focus on this, and this is where we'll end it for today. The central limit theorem states that for an arbitrary distribution with a mean mu and a variance sigma squared, we can draw n observations and calculate the mean of m subsets of those n observations, right? So basically we have a distribution function, which we don't know. It's arbitrary distribution function. It's not necessarily a Gaussian. It just has a mean mu and a variance sigma squared. We then draw n observations and we take the average of those n observations. And we do it again. We draw a new n. We average them. We do it again and again and again and again and again. And the central limit theorem says that the distribution of those means approaches the standard Gaussian, the 0, 1 Gaussian, or rather the distribution of the z-scores of those means approaches the 0, 1 Gaussian as n goes to infinity with certainty. That's a super remarkable theorem statement. What it means is that if you take the average of totally random observations, no matter what distribution they come from, those averages will be distributed in a Gaussian fashion. And that seems almost too good to be true, right? But we can actually demonstrate it really simply. So we can define a gamma distribution, a gamma variable, which follows the gamma distribution 1, 2, with shape parameter 1 and a scale parameter 2. And that distribution looks like this. And I think that we can all agree that's not a very Gaussian distribution. Okay, it's got a sharp cutoff at 0, and it's got a long exponential tail to high values. What now do we get if we take 2 observations of this random set of X observations and average them together, and then plot the average? And then we do it again and again and again and again and again, and we build up a distribution of averages. Yeah. Well, if we take sets of 2, we know that the expectation of this distribution is 0.5. If we take sets of 2 objects, 2 observations, then we end up getting the green line. Now that already is very, very much different to what we had in the red. If we take our observations 4 objects at a time, we get the blue, and we take averages of 4 objects at a time. If we take 16 objects at a time, we get the orange. And to give you an indication of how remarkable that convergence to the normal distribution is, we can take this distribution of means from the 16 observations taken at a time and just actually do the Z transformation on those averages and then compare it to the 0, 1 Gaussian. And this is what you get. So we took data that was in the form of an exponential distribution, a gamma distribution, and all we did was say, I'm going to look at these data 16 objects at a time, and I'm going to observe the expectation of those objects, and I'm going to plot the distribution of those variables. And all of a sudden, we've taken something that is highly non-Gaussian and ended up with almost a perfect Gaussian distribution. And this has a huge influence over the empirical sciences, the experimental sciences. And the reason it has a big influence, I know people are probably thinking, well, how often am I going to be interested in averages of a particular, number of subsets of observations? But the reality of the situation is that when we make observations, we are very rarely, almost never, observing a particular process independently. But instead, we're observing the result of many, many processes that have smashed together and produced the thing that we are observing. As a simple example, imagine a particle traveling through a box filled with other particles. Now, let's say that every single interaction that that particle has with another particle is governed by the gamma distribution. I'm not saying it is, but let's just make that assumption. It's a highly non-Gaussian interaction. But if that particle interacts with 16 or more other particles, and each time has the gamma distribution random draw imprinted on it, the net result is that that particle's energy distribution will be drawn from this Gaussian, not from the gamma distribution that it originated with. Okay, and this is profound. This is hugely important, and it basically means that the Gaussian distribution comes out of lots of different physical processes, and it comes up a lot in the experimental sciences for that reason, due exclusively to the central limit theorem. There's one other thing that's worth noting, though, about the central limit theorem, and that is the actual rate at which you converge to this Gaussian. So if we look at this distribution, what we'll see is that if we take the m equals 4 averaging, you can see the core of the distribution is already starting to look really Gaussian, even just with 4 combinations. But the tail of the distribution is still very exponential. And that's because the way in which convergence happens in this distribution is that the central or the observations closest to the expectation converge to the Gaussian fastest. And that means that if you have a distribution, an initial distribution with a long tail, then the parts of that distribution that converge to your 1,0 Gaussian in the z-score, the slowest, are the ones that are the furthest from the mean. And that means that when you're doing these, when you're computing or you make your assumption that you actually have a Gaussian distribution because of the central limit theorem, the parts of the distribution that don't conform to that assumption are the ones that are the furthest from the mean, right? And as we saw from our very beginning, at the beginning of this lecture course, those are the things, those outliers are the things that bias things like the standard deviation estimate of a Gaussian distribution. And so, even though the central limit theorem is remarkable, and the fact that you converge so rapidly to something that approximates a Gaussian, if your convergence is small because you have low n, for example, low number of combinations, then the parts of the distribution that don't converge are the ones that have the greatest sway over your summary statistics. And so making the assumption that you have a Gaussian distribution is not necessarily a safe thing to do, even though the central limit theorem exists. So, put simply, even though you can make this argument because of the central limit theorem, things converge to a Gaussian distribution, you should always pay attention to what's happening in the tails of the distributions, because they overwhelmingly govern what happens to summary statistics. And from the central limit theorem itself, we know that they're not that they are the thing that converge the slowest. So they will be pathologically present in your data with good reason. Cool. The last thing to observe is that given what we just said about the fact that the Gaussian distribution convergence to the central limit theorem is slow in the outliers, it therefore makes sense for us to, instead of saying, okay, yes, the central limit theorem is great, but is there a formula, is there a distribution that can take account of the fact that given a small number of combinations, n, I expect there to be many outliers. I don't expect it to have, I expect it to have a Gaussian core with outlier wings. And that distribution that does that is the student t distribution. So I won't go through this now. You can have a look at the lecture notes and read about the student t distribution if you like. Yeah, so basically, but put very quickly, the student t distribution is, if I actually run the experiment that I just did on the last slide again, but I now, instead of assuming a Gaussian distribution, I assume a student t distribution, then the distribution of averages here follows the solid line, the observed averages follows the solid lines. And the analytic expectation that you get from assuming that that distribution follows a student t distribution, not a Gaussian, is the dotted line. And you can see that they're extremely well matched. So the student t distribution is the thing that follows most closely what actually happens with the central limit theorem. And so it's very, very useful to quantify the distribution of parameters using this very flexible distribution, and actually is used quite extensively for determining how good, distributions of observations are compared to the expectation. It's actually one of the statistics that we're going to use when we get into model fitting for determining whether or not a distribution is a good fit to the data. And crucially, the student T has these long wings because we expect them to be there because of the central limit theorem in the limit of low n. As you go to many, many n, m of 100, for example, the student T becomes the Gaussian distribution or converges to the Gaussian distribution. All right, we have 2 more distributions to talk about, but we can talk about them at the beginning of next week. So I think we will leave it there. Not next week, obviously, because next week is a break. So we will see one another again in 2 weeks' time. Yeah. And we will continue with the last lecture on probability, and we will finish these last 2 distributions, and then we'll talk about what's so the next lecture is going to be all about what's things like Monte Carlo simulation and why is it useful and things like that. Great. All right. As always, please feel free to ask questions. I'll upload the lecture notes up to this slide to the Moodle, and we will see each other in 2 weeks' time. Have a good break and a relaxing break.
Thanks. Bye.
Thank you. Bye.
Bye.
Bye.